Hello friends, today I'll be discussing the topic Digital Protection of Transmission Line. My name is Chaitanya Jadkar and I am a student of PVG College studying for Masters of Engineering. The content of my presentation are as such. I'll be introducing you to the topic, then I'll be explaining the protection scheme of transmission line. Then I'll be discussing the digital protection based on fundamental signal. Introduction. During past decades, overcurrent relays were used for protection of transmission line. They had certain disadvantages that I'll be discussing further. Next came the distance relays. Now these relays were electromechanical relays. If there is a current flowing through the relay coil, it will generate its own flux and will hold on the switch. As soon as there is a fault, the current through the relay coil would vanish and so would the flux, releasing the switch. This was the basic operation of these electromechanical distance relays. They too had their own disadvantages. Basically, due to mechanical structure, it ended into problems. Also, due to inclusion of instrumentation transformers for these relays, it will overload the system itself. So as a solution came the static relays. Now static relays were programmable relays, but they too had disadvantages. Basically, static relays were high speed, low burden, and of course less maintenance. But they were only once programmable. With changing complexity of the power system, they could not be reprogrammed. If they were supposed to be reprogrammed during 1930s when actually they came into existence, the computer structure was so complex that it would have been more tedious. Also, manual errors would have been introduced. G.D. Rockefeller in 1965 introduced for first digital relaying scheme. And so was born the modern digital world. It was more compact, reliable, and efficient. We'll see the structure of it. The basic structure of a numerical relay was as such. The CT and PT would capture the analog signals from the power system and would lead it to the further elements of this scheme. The explanation of blocks will not be held in this presentation. The flow is as such. The analog signals captured by CT and PT will be sent to anti-aliasing filters. Next came couple and hold circuit, the multiplexer, and lastly analog digital converter that will be sending the digit to your microprocessor or DSP, that is digital signal processor chip. After going through the programming in the DSP, if there is a condition of tripping, the command will be sent to the power system circuit breakers. The elements in this hardware design are as follows. CT and PT for data acquisition. Transactors are the transformers for addressing AC and DC outputs from CT and PT. Active band filters. Sample and hold circuit for holding the sample until ADC programs its input. Multiplexer for selecting appropriate input signals. ADC for analog to digital conversion. DSP for entire programming and control of this hardware scheme. And the tripping circuit that sends relaying command for the circuit breaker to trip. Transmission line protection scheme. In past days, overcurrents were used for protection scheme of transmission line. They had some shortcomings above 50 kV, that is shift of balance point or the reach of the relay. Now this was due to the changing type of faults, the change in generation capacity, and the switching of loads, which is random. So distance relaying scheme was introduced. Also, relaying scheme based upon wave phenomena was introduced. Distance relaying scheme includes the following 4 points. First, Fourier analysis with one cycle data window. One cycle data window means the input of only one cycle is taken into consideration. This reduces the processing time of the processor. This scheme was first introduced by Mr. Ramamurthy. In this, the incoming samples of voltage and current, sinusoidal and cosine waves were correlated with already stored samples of sine and cosine waves. The formula for sinusoidal voltage and cosine voltage is given as such, where n is the number of samples in one cycle. Similar to this, the magnitude of sinusoidal and cosine currents will be calculated, using which the impedance of the line was calculated. Predictive calculation of peak values. In this, we calculate impedance from peak values of voltage and current. Now at any time t, the voltage is given by this formula. Taking its derivative, we get this. Now shifting the omega on the left hand side and squaring, we get the following equation. The angle of this peak voltage is given by this formula. Same thing can be calculated for the peak current. From these peak values of voltage and current, the impedance can be calculated with the following formula. The angle of this impedance is given by alpha. Digital protection based on fundamental signal. Before fault or pre-fault, normal sinusoidal excitation exists over the bus. After the fault, or that is transient fault, the transient waveforms and DC offset are also introduced into the voltage. Transients and DC offset can be eliminated by programming in relay by introducing proper filter. So the tripping criteria for this scheme is Z if is less than the Z nominal or set impedance. The tripping command will be sent to the circuit breaker. The main question arises is how to set the Z nominal. Now consider a line with an impedance of 1 ohm per kilometer. Consider the length of the line as 10 kilometers. So the total impedance becomes 10 ohm. Consider a fault the right end of the line with respect to relay 1. In that case, the CT and PT will send values to the relay and the impedance can be calculated equal to 10 ohms. Now consider a fault in exactly the center of the line. In that case, again CT and PT will send values to the relay and the impedance is calculated as 5 ohm. Now using this relation, we can actually design the settings for the distance relay. So what impedance of the line should be considered under protection by relay 1? 30%, 40%, 50%, 70%, 80% or entire 100%? Of course the answer is entire 100%, but Z nominal is usually not set to the 100% of the line impedance. This is because we have to consider the variation in impedance of the line with changing factors. Let's consider the weather. Transmission line is not always under constant weather conditions like humidity, cloudy weather, and warm or sunny weather. Other impedance variation factors are inaccuracy of CT and PT ratios, ambiguity about line parameters, DC offset in fault current which changes the impedance with its own existence, transient response of capacitive voltage transformer. For more details, you can Google this. Now setting the value of Z nominal. So basically, the relay 1 does not occupy the entire 100%. Instead, it occupies 80 to 90 or 70 to 90% of the entire length of the transmission line as zone 1. But from relay 1, we have to protect the entire 100% of the line. So the entire zone 2 has to be protected. Why do we not set the entire 100% impedance under protection. Consider transient overreach problem. Now in this, consider fault at point X, that is at distance X from point A. Now when there is no offset current in the system during the fault, consider a nominal setting of impedance as 10 ohm. Now in case of fault at 10 ohm, voltage is 100 volts and current is 10 amperes. Therefore, impedance will be 10 ohms, which is equal to the Z nominal settings and also has a tripping criteria. So, the relay will send the tripping command to the circuit breaker. Now, consider another fault at 12.5 ohm distance from A. And there is a presence of DC offset current in this case. Again with a setting of 10 ohm, a fault at 12.5 ohms. Voltage will be 100 volts, current will be 8 amperes as calculated. Assuming DC offset current of 6 amperes, the RMS current becomes 10 amperes. Therefore, the exact impedance at that point is equal to voltage divided by current 10 ohm, which is also equal to the tripping criteria, even if the actual impedance of the line was 12.5 ohm. So, even in this case, circuit breaker receives the tripping command. Now, this was the concept of transient overreach, which was more than the 100%. So, if we set the value to 100%, it will vary or extend up to 120% of its entire length. The better the design of relay, the better is the transient reach. Relay designers have not been able to reduce it below 10%. It is usually 10 to 20%. Hence we implement 3-step protection scheme. Now consider the setup for 3-step distance protection. The line under protection is line AB between bus bar A and B. Protection scheme for line AB is given by relay A just adjoining bus bar A. This is zone 1, that is 80 to 90% of the entire considered line. Zone 2 is considering entire length of AB and 50% of the adjoining line BC. Zone 3 is considering entire distance between A and C and also exceeding to 20% of the next line. The tripping criteria for these zones are as such. For zone 1, there is instantaneous tripping. For zone 2 and zone 3, the timings are T1 and T2 respectively. T1 and T2 are decided as such. For zone 1, it is instantaneous. For zone 2, the operating time of zone 1 plus some selective time interval, which includes the operating time of circuit breaker and the time travel of the relay signal. Also, for zone 3, the time is selected in similar fashion with respect to zone 2. The exact value of tripping is as such. For zone 1, it is instantaneous. For zone 2, it is 0.3 to 0.5 seconds delayed. And for zone 3, it is 1 second delayed with respect to zone 1. Let us consider the concept of shortest adjoining line. Here, line AB is the primary line under protection. BC and BD are adjoining lines of line AB. BC is longer than line BD. So the shortest adjoining line is line BD with respect to line AB. Let's zoom into that section. These are the zones of relay RA and relay RB. Both have different protection scheme relays. Now, if the timing of both these relays with respect to zone 1 and zone 2 are same, and if there is a fault as shown between the two lines, in that case there is a clash between zone 2 of relay A and relay B having same timings. In this case, both relay A and B will trip together, which is not desirable, as only relay B should operate in this case. This fault occurred because the 50% of the longer adjoining line was considered for zone 2 of relay A. Instead, the relay should select 50% of the adjoining shortest line, that is line BD. In that case, the zones will not clash and only relay B will operate. Operating time for this is selected in the similar fashion as discussed earlier. 3-step distance protection using more relay. Basically, this tells us the numerical settings of the zones. The line cutting the edges of these circles gives us the exact values of the zones' impedances. Thank you.